Hi friend, welcome to Math A to Z. Today we discuss some important MCQ type question of Riemann integration. Now we start with a question. First question of the class is: let fx equal to 0 for x irrational and 1 for x rational. Then integration a to b upper bar fx dx equal to b minus a. B, integration a lower bar to b fx dx equal to 0. Option C, integration a to b upper bar fx dx equal to 0. And the last option D, integration a lower bar to b fx dx equal to b minus a. Fx equal to 0, x rational equal to 1, x irrational. So for the Riemann integration of any interval AB, if we partition this interval by any number of points, and we know that in each of the subinterval contains infinite number of rational points as well as irrational points. So in each interval, if interval length is del xr, rth subinterval length is del xr, then the supremum of the function fx in del xr is equal to 1 and infimum is equal to 0. So from the definition of lower Riemann integration and upper Riemann integration, we know that integration a lower bar to b fx dx equal to summation small mr into del xi, right? Small mr into del xi, and it's obviously it's supremum. Obviously it's supremum. Then this is equal to supremum of summation 0 into del xr, that is equal to 0. And this is in our question, option, here is option B. And upper Riemann integration, definition of upper Riemann integration, infimum of summation mr into del xr, and this is infimum of 1 into del xr, that is infimum of del xr, summation of del xr means b minus a, total length of the interval, that is b minus a, since this is constant, and this is in the first option. So the option A and option B are correct. If the function f is defined in the interval open 0 1 as fx equal to root 1 minus x square when x is irrational, 1 minus x when x is rational, then option A fx is not R integrable in open 0, 1. The lower Riemann integral of f is half. The function f is Riemann integral of f is pi by 4 and the function is not R integral. I think the option C is wrong. The upper Riemann integral of f is pi by 4. Fx equal to root 1 minus x square, x irrational, and 1 minus x if x rational. Now we know that root 1 minus x square minus 1 minus x whole square is equal to 1 minus x square minus 1 plus 2x minus x square. That is this and this is not cancelled, this cancel and 2x minus 2x square, that is 2x into 1 minus x. This is greater than 0 because we examine the Riemann integration of x belongs to 0, 1. So from this condition we can write in any subinterval of 0, 1, any subinterval of 0, 1, this is if del xr. Here capital MR equal to, this is greater than 0, that is this greater than this, and root 1 minus x square, 1 minus x. Capital MR equal to root 1 minus x square and small mr equal to 1 minus x. Right? Now we calculate the upper integration and lower integration. That is integration 0 lower bar to 1 fx dx equal to integration 0 to 1. This is 1 minus x into dx. Right? 1 minus x into dx. And this is equal to x minus x square by 2, that is 1 minus half, that is half. And if we calculate upper integration 0 to 1 upper bar, this is equal to 0 to 1 root over 1 minus x square dx. And this means x by 2 into root over 1 minus x square plus half sine inverse x, 0 to 1. So this is 0, 1 half into pi by 2, that is pi by 4. And here option A is f of x is R integrable on 0, 1. So this is not R integrable since half not equal to pi by 4. This is not R integrable, so A is not correct. Option B, the lower Riemann integral of f is half, that is B is correct. And also C is correct. This is given that upper integration is pi by 4. And the last option, the function f is not R integrable. This is also correct since it is not R integrable. The oscillation of a bounded function f on an interval closed AB is option A, supremum of the set mod of f of x1 minus f of x2 such that x1 x2 belongs to closed AB. Option B, infimum of the same set. Option C, both A and B, and option D, neither A nor B. Here we get capital M and small m are the supremum of f of x and infimum of f of x in AB, right? So we get f x1 less equal to m greater equal to n, and also f x2 for all x1 x2 belongs to m. That is f of x1 minus f of x2 less equal to m minus m, this. So m minus n is the upper bound. Now from the definition of this and definition of this, for any PSI in epsilon greater than 0, there exists x dash x double dash belongs to A such that here capital M is in this position and small m is in this position. So if we subtract some epsilon by 2, m minus epsilon by 2, then there exists x dash such that f x dash greater than m minus epsilon by 2. That is f x dash greater than m minus epsilon by 2. Similarly, if we add epsilon by 2 with m, then there exists x double dash such that f double dash less than m plus epsilon by 2. Now f x dash minus f x double dash greater than m minus m minus epsilon. And if we take this, so this is also right. Now from the condition this and from the condition this, we say that m minus m equal to supremum of mod of fx1 minus fx2 such that x1 x2 belongs to AB. Correct? And this is the option A. This is the option A. And option B is infimum of, so it is wrong, B is wrong, B not correct. And both A and B, these are all also not correct, and neither A nor B, and this is also not correct. So the option A is only. Which of the following is or are correct? Option A, if a function f is monotonic on closed AB, then it is integrable on closed AB. That is means are integrable. Option B, if a function f is continuous, then every epsilon greater than 0, there exists delta greater than 0 such that mod of summation I equal to 1 to n f of ti into delta xi minus integration a to b fx dx less than epsilon for every partition p of closed AB with non p less than delta and every choice of points ti in xi minus 1 to xi. Option C, exactly one of A and B, and option D, none of the above. The first option is, if f of x is monotonic in AB, then it is integrable on AB. F of x is monotonic in AB, then f of x belongs to R, and this is the correct option. We know that this is an important theorem and main theorem of R integral. If the function is monotonic, either monotonic decreasing or monotonic increasing, in both cases the function fx is R integrable on AB. So A is the correct option. And before we going to the option B, we define another definition of R integrable. If we make a partition of AB, this partition, and let this is xr minus 1 to xr, this, and this is del xr equal to xr minus 1. And if we choose xi r in each of the subinterval, xi r any point in each of the subinterval, then we get a sum f of xi r into del xr, where r equal to 1 to n. And if there exists a number capital A, this is the integration AB fx dx. For any epsilon greater than 0, there exists delta greater than 0 such that norm of P, this is the partition P and this is the norm of P. Norm of P less than delta, for which if summation r equal to 1 to n f of xi r into del xr minus a less than epsilon, then we say that the function f of x is R integrable in closed area, and a is the integration value of the integration. So the option B is also correct, since here given if the function fx is continuous, then for every epsilon greater than 0 there exists delta greater than 0 such that mod of summation I equal to 1 to n f of ti into del xi minus integration a to b fx dx less than epsilon for every partition P of AB with norm P less than delta, and for every choice of point ti in xi minus 1 to xi, that is in the ith subinterval. So it is also correct. So option A and option B are correct, and the option C is exactly one of A and B, and option D is none of the above. So C is not correct and D is also not correct. Here two statements are considered. Statement 1. A bounded function f having a finite number of points of discontinuity on closed AB is integrable on closed AB. And 2. A bounded function f is integrable on closed AB if the set of points of discontinuity has only a finite number of limit points. Then option A, 1 is true but 2 is false. Option B, 1 is false but 2 is true. Option C, both 1 and 2 are true. And option D, neither 1 nor 2 is true. Here two statements are given. The first statement states that a bounded function fx having finite number of points of discontinuities on AB is integrable on AB, and this is correct. This is important theorem of R integrable. And the second statement, if the point of discontinuities have only finite number of limit points, then fx belongs to RAB. That is, fx is also R integrable on AB, and this is also correct. This is two consecutive theorem and very important theorem of R integrable. So here the option A, 1 is true but 2 is false, that is not correct. Option B, 1 is false but 2 is true, this is not correct. Option C, both 1 and 2 are true. This is correct. And neither 1 nor 2 is true. This is false. Consider the function fx equal to 0 when x is irrational or 0, and 1 by q when x is any non-zero rational number p by q with least positive integer p and q. Then f is R01, that is f is R integrable in 0 1. Option B, integration 0 to 1 fx dx equal to 0. Option C, integration 0 to 1 fx dx equal to p by q for q not equal to 0 and p q belongs to z. And option D, none of the above. Fx equal to 0 when x is irrational and 1 by q when x is rational of the form p by q with least positive integer p and q. And we test the R integrability of f of x in the interval 0 1. We have for any epsilon greater than 0, if it is given, then there exists a large q belongs to capital N such that 1 by q greater than epsilon by 2. That is for epsilon less than, that is for q less than epsilon by q less than 2 by epsilon. And we rename this type of point p by q, x equal to p by q, which is a rational point, for which 1 by q greater than epsilon by 2 as exceptional point. Exceptional points. Okay, and all the other points of the form p by q, here 1 by q less than epsilon by 2. But exceptional points are finite in number, and all the other rational points of the form x equal to p by q, in which 1 by q less than epsilon by 2 is infinite in number. Now the oscillation, now we make a partition of the interval 0 1. This is any partition P of 0 1. We know that for any partition of 0 1, in any subinterval there are infinite number of rational points and infinite number of irrational points. So in each subinterval the infimum of f of x equal to 0, obviously 0. And supremum of f of x is equal to 1 by q, where p by q belongs to this subinterval. The maximum value of 1 by q. Okay. Now in any interval where no exceptional point include, okay, no exceptional point include in any subinterval, then the oscillation of f of x in this subinterval clearly 1 by q minus 0, that is less than epsilon by 2. And if in any subinterval which includes at least one exceptional point, then the oscillation of f of x in this subinterval is at most 1. Okay, because the oscillation, total oscillation of the function is 1. Now since the exceptional point is infinite in number. So we make a partition such that the subintervals, the total length of the subintervals containing the finite number of exceptional point is less than epsilon by 2. Okay, here oscillation is at most 1 and total length of the subinterval is epsilon by 2. And here the oscillation is epsilon by 2 and total length of the subinterval is maximum 1. So the total oscillatory sum, that is UPF minus LPF, of the function f of x in the interval of 0, 1 is given by UPF minus LPF less than epsilon by 2 plus epsilon by 2, that is epsilon. So we say that it is R integrable. Okay, so the option A is correct. Yes, this is option A. Option A is correct. And since f is R integrable, then the lower integration and upper integration are same, and we can easily calculate the lower integration. That is, lower integration is integration 0 lower by 2 1 fh dx. This is equal to 0 dx equal to 0. So the value of the integration is 0. Integration 0 to 1 fx dx equal to 0. So the option B is also correct. And obviously option C and option D are not correct. Last question of the class is, consider the function f defined as follows. Fx equal to 1 by 2 to the power n when 1 by 2 to the power n plus 1 less than x less equal to 1 by 2 to the power n, where n equal to 0, 1, 2 dot dot and 0 elsewhere. Then option A has infinite number of point of discontinuity. Option B, f has finite number of point of discontinuity. Option C, the set of point of discontinuities of f has only one limit point. And option D, every member of set of points of discontinuity of f is a limit point. Here the function is fx equal to 1 by 2 to the power n such that 1 by 2 to the power n plus 1 less than x less equal to 1 by 2 to the power n equal to 0, 1, 2 and 0 elsewhere. And we write the function as fx equal to, if we put n equal to 0, then this 1, then this 2 and so on. Clearly this function at the point x equal to half, lower limit is 1 and upper limit is half. So it is not continuous at a half. Similarly, it is not continuous at half square. Similarly, it is not continuous at half cube and so on. So the point of discontinuities are half, square, cube, n and so on. So obviously the function has infinite number of point of discontinuities, and this is given in option A. So the option A is correct. And this set has only one limit point, 0. Clearly this is 0 is the limit point of this set, because if n tending to infinity, then half to the power n tends to 0. So this set has only one limit point, which is 0. And the option B is T has finite number of point of discontinuities. B is not correct. See, the set of points of discontinuities of f has only one limit point, right? This is C. And option D, every member of the set of point of discontinuities of f is the limit point. No, half, half square, half cube are the not limit point of this set. Okay, so D is not correct. So the option A and C are correct. Okay, this is the today's class. Thank you for watching. Thank you very much.